Hello class, welcome to exercise 3A, Irrational Numbers including Surds. I hope that this class makes a lot more sense than the name suggests. In this class, your pre-learning is going to be example 1, defining and locating surds. And your pre-learning will be questions 1 and 2 in the new book and question 3 in the old book. Then we'll be doing example 2, where we'll be simplifying surds. And for this example, your pre-learning will be questions 4, 5 and 6 in the new book and questions 5, 6 and 7 in the old book. And then in example 3, we'll be expressing as a single square root of a positive integer. And for this example, your pre-learning will be question 7 in the new book and question 8 in the old book. With this being the first lesson of a block, as usual, it means there'll be a little bit more in the introduction. And it's your choice on how you prepare to succeed in this lesson, but there's nothing wrong with simply watching the first time round and not taking down any notes until after you've completed the pre-learning. I won't be that surprised if the algebra doesn't make total sense to you until you've tried the numbers. But of course, unlike a normal class, you don't have to wait for me at any point either. You can jump backwards, forwards, skip, repeat, do whatever you want. But let's get on with the introduction for this lesson and the topic as a whole. So what is this? This thing that we call the square root. We know that the square root of 4 is 2 and the square root of 9 is 3. And we also know that 2 squared is equal to 4 and 3 squared is equal to 9. But before we really explain it, let's go back to the start of maths, just like we did with the exponential. So just as a plus b means count b from a, and an easy numeric example is 2 plus 4, which is starting at 2 and then counting forwards 4. We also know that a times b means b groups of a added together. And a numeric example is 4 times 2, which is adding 4 groups of 2 together, and that equals 8. And as we've already covered in this unit, a to the power of b means ba's multiplied together. And a numeric example would be 2 to the power of 4, which is equal to 4 2's all multiplied together, which equals 16. So while other symbols we've learnt throughout the years actually translate to a short sentence rather than a word, so does square root. So if the square root of a equals b, that just simply means b squared is equal to a. One example is the square root of 9 is 3 and 3 squared is 9. Other than square roots, we've also got these things called cube roots. So if the cube root of c equals d, then d cubed equals c. And a good example of that is the cube root of 64 equals 4 and 4 cubed equals 64. So sticking to the same a, b, c's and d's here, if we were to substitute b squared in for a, because we've already established that b squared equals a, and then substituted in d cubed for c, we'd end up with the square root of b squared is equal to b, and the cube root of d cubed is equal to d. So using the same numeric examples, 3 squared is equal to 9, so the square root of 3 squared is equal to 3, and 4 cubed is equal to 64, and we know that 64 cubed is equal to 4. Also, if we were to begin with the statement the square root of 9 is equal to 3, then square both sides and evaluate 3 squared to be 9, and realize 9 is 9 to the power of 1. So therefore we've shown that the square root of 3 squared is equal to 3, and the square of the square root of 9 is equal to 9. And similarly with the cube roots, if we started off with the statement the cube root of 64 is equal to 4, and then cube both sides, and then evaluate 4 cubed to 64, well 64 is just 64 to the power of 1, right? So the cube of the cube root of 64 is equal to 64. So using the concepts of third index law, it actually turns out that the nth root, which could be any number, not just 2 or 3, raised to the power of n of b is actually equal to b to the 1. So because of the third index law, this actually means that the nth root of x is equivalent to x to the power of 1 divided by n. Because the third index law says we multiply the power in the brackets times the power outside of the brackets. And 1 on n times n is equal to 1. So even though it's not explicitly stated with the square root, this actually means that the square root of a is equal to a raised to the power of a half, because we're obviously using squares to neutralize the square root. For For the rest of this unit, we'll only be working with square roots, but this concept of nth roots is vital for our next unit in exponentials, which we'll be doing in semester 2. Rewriting the expression we used about the third index law, in relation to square roots, we still get the same result, but there is a catch, and that is x has to be greater than or equal to 0. So the question is, why greater than 0? Well, this is because there is no square root of a negative number. Because if x was equal to the square root of negative 2, then x squared has to be equal to minus 2. However, because a negative times a negative is positive, and a positive times a positive is positive, and 0 times 0 is 0, then any number squared is either positive or 0 for all real numbers. There does exist numbers that can be multiplied together to equal a negative number, but it's probably a little bit complex to imagine what they are right now. I should also mention there's one other catch involving negatives. Because the square of a negative number is a positive number, then when we use an actual numeric example like the square root of 4, well, that could be 2 or minus 2, because minus 2 squared is equal to 4, right? Then we use this fancy term to say that the square root of 4 is equal to plus or minus 2. But for this unit, we're just going to assume the square root of x is positive. Now, because the square root of a is actually equal to a raised to the power of a half, this means that we can use index laws 4 and 5, which means that the square root of a times b is equal to the square root of a times the square root of b, because that's the same as saying a times b raised to the power of half is equal to a raised to the power of a half times b to the power of a half. And law 5 says the square root of the fraction a over b is equal to the fraction of the square root of a divided by the square root of b. Because by law 5, the fraction of a over b raised to the power of a half equals a raised to the power of half over b to the power of a half. So obviously the first line there was law 4 and the second line was law 5. So this use of law 4 and 5 is very important for the rest of this unit and for nearly all other units for the rest of the year. In the lesson title, we have this word surds. So what are surds? So it turns out that square roots are our first introduction to what we know as irrational numbers. Finding square roots of perfect squares are easy. And it should be obvious to you that if x is bigger than y, then the square root of x will be bigger than the square root of y. And if I was to draw a number line that went from 1 to 2, then we know that 1 is the square root of 1 and the square root of 4 is at 2. So where does the square root of 2 and the square root of 3 go? Here's something I printed up with GeoGebra earlier. So this is the number line starting at 0. You can see the square root of 0, and you can see that the square root of 4 is on 2, and that the square root of 2 and the square root of 3 is between 1 and 2. But what is that actual value? Because they're sitting on the real number line, root 2 and root 3 are definitely real numbers. In fact, root 2 is something that pops up in the most simple of triangles and has been known since the time of Pythagoras. And that triangle is your right angle triangle, where there's two sides of length 1. The other side, some length x, can only be found with the Pythagorean equation a squared plus b squared equals c squared. In this case, that is x squared equals 1 squared plus 1 squared, which is the same as saying that x squared is equal to 2 or x is equal to the square root of 2. This baffled the Pythagoreans for a long time, but then a man by the name of Hippasus found that the square root of 2 can't be expressed as some fraction a over b, where a and b have no common factors. In other words, a fraction that can't be reduced anymore. So this means that there's no ratio to express root 2, and so this is why we call it irrational. And it turns out that the root of all numbers that are not perfect squares are also irrational. So these are the numbers that we call surds. But please treat them with respect, because poor old Hippasus was murdered for having ruined the Pythagorean philosophy that all things and all numbers were in ratio to each other. Before you continue on, I have a little challenge for you, and part A of that is find a number x where x squared is equal to 2. The trick with that is to try and estimate different numbers until you get closer and closer. Alright, and in part B is not a challenge to do now, it's just letting you know that the enrichment section of this exercise is a step through the proof of why root 2 is irrational, that there's no fraction to represent it. Also, I've got a great video here from Mathologer that might be a bit tricky for some of you, but I really like it, and it goes through a visual proof using squares and marching people to show why root 2 is irrational. And I'll leave that link here. You can follow that video if you want. So when the Pythagoreans discovered irrational numbers, they were thinking about ratios or fractions. But in modern times we use decimals, and it turns out the rational numbers are represented as terminating or recurring decimals. So for example, 3 on 2 is equal to 1.5 and 78% is equal to 0.78. And you can see that their decimal expansion terminates. Whereas 1/3 is equal to 0.33333, and that's definitely recurring. It's really important to note that just like we saw with surds, all irrational numbers and rational numbers can be placed on the number line. So for example, we know that the number pi is just a little bit more than 3. We know that 5 on 2 is the same as 2.5, and 37% is a little bit over 1/3. And I happen to know that the square root of 2 is around about 1.5, a bit less than 1.5. Just notice how I've got negative root 2 is written as the negative times the positive root. Alright, so just at this point note that some ideas covered in this introduction will not be covered in the examples in this lesson. However, all these ideas are needed for the whole unit. So I suggest you revisit this lesson throughout the unit to take some more notes as you go. Anyhow, let's move on to the sections that contain the examples. In this section, the task will be defining if surds are rational or irrational, and then locating them on the number line with some rational numbers. Looking at rational numbers on the number line is fairly easy. However, we'll need to estimate surds. So for example, estimating root 2. So what number squared is 2? So we know the square root of 1 is equal to 1, and the square root of 4 is equal to 2. So that means that the square root of 2 has to be somewhere between 1 and 2. So my first guess is 1.5, and that squared is equal to 2.25. So it has to be less than 1.5. So 1.4 is equal to 1.96. So that's 1.4 squared. And that's less than 2. So the square root of 2 has to be more than 1.4, but less than 1.5. So we can try 1.41 squared, which is equal to 1.9881. So it's obviously more than 1.41. So let's try 1.45. So you can see that's getting very close. And so it's definitely around about 1.41. So yes, these numbers are getting closer and closer. However, I can assure you it's going to take infinite time to find the whole decimal expansion. And that's because it's an irrational number and they have infinite decimal expansion. However, I've got a web link here where NASA has evaluated the first 1 million digits. So clearly the square root of 2 is equal to 1414213. Oh my goodness. Let's have a scroll through them. Anyhow, that's enough time for me. For those of you who are crazy enough to go through it all, here is the link. Sometimes you have a calculator on hand and a calculator does a good estimation. So let's use the OneNote version. We can see the calculator estimates it to be around about 1.4121. Also note that funny looking equal sign, that means approximately. If there's no calculator on hand, you can use the concept I was using before and estimate by perfect squares. So for example, the square root of 25 is 5 and the square root of 36 is 6. So that means that the square root of 26, 27, 28, 29, 30, 31, 32, 33, 34 and 35 are all between 5 and 6. Anyhow, let's get on with example 1, where we need to express each of the following numbers as a decimal, and then decide if it's irrational or rational. Once we finish with all the numbers, we're going to locate them on the same number line. So part A is minus square root of 3. Alright, so 3 is not a perfect square, and so therefore the square root of it is a surd, so it's irrational. And using OneNote to evaluate that, we get minus root 3 is approximately minus 1.732 yada yada, and we should write that out. Alright, part B, the number is 137%. Okay, so the definition of percentage is dividing by 100. So that equals 137 divided by 100. And dividing by a power of 10 is easy, and it's going to move the decimal place, so that now becomes 1.37. So because it's a fraction, and because it's a terminating decimal, it's definitely rational. Right, in part C, we've got 3 divided by 7. So to write that out as a division, that's equal to, and to quickly do that division, it becomes, so as I've come back to 4 again, I know this is going to recur over and over again, because eventually I will get back to 4 over and over again. That means that 3 on 7 is equal to 0.428571 recurring. And that is definitely rational because it's recurring decimal. It should also be obvious that it's rational because it was written as a fraction. All right, let's draw that number line. And I don't need less than -2 or more than 2 because there's no numbers outside those. So our minus square root of 3 was -1.7, and 137% was around about 1 1/3. And 3 on 7 is close to a half, just a little bit less. So there you go, all those numbers are on the number line. All right, so for you to go ahead and practice this skill, you should pause the video now and work on questions 1 and 2 in the new book and questions 3 in the old book. And I'll see you in the next section. All right, in this section, we're simplifying surds. And the reason we're going to do that is because sometimes we need to find the length of the surd. And it might be simpler to rewrite that surd as a whole number times a smaller surd. As we mentioned in the introduction, we know that the square root of a times b is equal to the square root of a times the square root of b because of law 4 in the index laws. If a number had a perfect square as a factor, so let's say x is equal to y squared times z, then the square root of x is equal to the square root of y squared times z. And using law 4, we know that's equal to the square root of y squared times the square root of z, which is equal to y times the square root of z because of law 3. So when we're simplifying, we need to find a perfect square factor. So you might want to know, where is the square root of 8 on the number line? Well, we know that 8 is equal to 4 times 2, and 4 is a perfect square. So this could make root 8 easy to understand because we know that the square root of 2 is approximately 1.41 and a whole other stuff. And using the factors of 8, the square root of 8 is equal to the square root of 4 times 2. And now we know that the square root of 4 is 2, so that's actually equal to 2 times the square root of 2. So using these two facts together, then the square root of 8 must be approximately 2.82. And that makes sense because we know that the square root of 8 has to be between 2, which is 4, and 3, which is the square root of 9. It's worth highlighting that we can only simplify a surd if the number in the square root has a perfect square as a factor. Okay, so let's try this out with example 2, where we need to simplify the following surds. Our surd for part A is the square root of 32. So we know it's a surd because 32 is not a perfect square. And we need to ask the question, is there a square factor? So can I divide 4 into it? Yes, I can. Can I divide 9 into it? No. Can I divide 16? Yes, I can. And it's 16 times 2, so that's the biggest square that I'd fit in there. So we'll leave it at that. So I can rewrite this square root of 32 is equal to the square root of 16 times 2, because 16 is a square factor. Then using law 4, that's equal to the square root of 16 times the square root of 2. And the square root of 16 is 4. We've obviously chosen it because it's a perfect square. So I can now rewrite that as 4 times the square root of 2. So this is the square root of 32 simplified as best as possible. All right, in part B, the surd is 3 times the square root of 200. So 100 is definitely a square, it's 10 squared, so I'm going to rewrite that as 3 times the square root of 100 times 2, which is 3 times the square root of 100 times the square root of 2. And as I said, the square root of 100 is 10, so that's 3 times 10 times 2. Sorry, that's the square root of 2. And 3 times 10 is 30, so the best we can simplify this is 30 times the square root of 2. So let's move on to part C, where our surd is 5 times the square root of 40, all divided by 6. So 40 has factors 10 and 4, so 4 is a perfect square and it's definitely a factor of 40. So I can rewrite that as 5 times the square root of 4 times 10, all divided by 6. And therefore the square root of 4 is 2, so I'm going to skip to the next step. And 5 times 2 is 10, so we've got 10 times the square root on 6. And I can divide 2 out of 10 and 6, so we end up with 5 times the square root of 10 on 3. All right, and the final one is part D, and that's the square root of 75 on 9. So we can automatically use rule 5. So that's actually equal to the square root of 75 divided by the square root of 9. And we've already got the square root of 9 simplified because that's a perfect square. But let's think about any squares that divide into 75. So 4 definitely doesn't. 16 definitely doesn't. 9 does not. And 25 does. So that's equal to 25 times 3. All right, so that's now equal to the square root of 25 times 3 on 3, because the square root of 9 is 3. And then the square root of 25 is 5, so I can just quickly throw that at the front now. So that's equal to 5 times the square root of 3 on 3. I'll just write because the square root of 25 times 3 is equal to the square root of 25 times the square root of 3. And that's as simple as we can get that. All right, I hope you'll find those quite simple, but let's practice. So let's pause the video now. And students with the new book can work on questions 4, 5, and 6. And students with the old book can work on questions 5, 6, and 7. And I should say the first bunch of numbers are for the new book and the other bunch for the old book. All right, so I'll see you in the next section then. So this section has a terrible mouthful of a name that I know sounded terrible in the introduction. But basically, in the last section, we simplified surds. So we would turn the square root of 8 into the 2 times the square root of 2. Now that's because if we're trying to measure something or understand where a number is on the number line, then 2 times root 2 is simpler. But sometimes when we make equations, it is much easier to work with the square root of 8. So using law 4 again, we just need to recall that as a is equal to the square root of a squared, then a times the square root of b is equal to the square root of a squared times the square root of b, which is equal to the square root of a squared times b. So this is just basically expressing law 4 in the opposite direction than we did in the last section. Anyhow, let's go straight on to example 3, where we're going to express the following surds as a square root of a positive integer. Okay, in part A, we've got 2 times the square root of 5. So 2 squared is 4, so 2 is equal to the square root of 4 squared. And we can now write our next line as the square root of 4 times the square root of 5, which is equal to the square root of 4 times 5, or the square root of 20. In part B, we've got 7 times the square root of 2, and the square of 7 is 49, so we can rewrite 7 as the square root of 49, and we can write it all out as the square root of 49 times the square root of 2. And 2 times 49 is 98, and so that's equal to the square root of 98. Okay, so it really is that simple. You just need to express the surd as the square root of one positive number. Anyhow, here's your chance to practice. Pause the video now and do question 7 in the new book and question 8 in the old book. And I'll see you in the summary. So this topic is key to being successful in many other units this year. Exponentials and the nth root are fundamental to logarithms, and surds are fundamental to quadratics and parabolas. And I shouldn't forget that surds are also very important to circles as well. So it's very important that you work hard at these skills for future lessons as much as this one. And nearly every lesson for the rest of this unit is just an extension of what we've learnt today. So to know you're successful in this lesson, you will know the meaning of the terms rational number, irrational number, and surd. Know how to identify a number as rational or irrational. Know the simple rules related to surds. Be able to simplify surds using the highest square number factor. Okay, I've decided to add one more challenge, and this is to test what we know about simplifying surds and the problems with negative numbers in surds. And we can check this in class, okay? So here it is. Convert -3 times root 5 into the square root of a positive integer and place it on the number line. All right, have a great day, and I'll see you later.